Hello, hello. This week's video is just going to be a recap of a few of the the two main ideas from the readings. A lot of this hopefully will be clear to you already from sort of the videos and the readings. But this is my take. Sometimes it's helpful to hear a few different versions, and I'm going to talk a little bit about some of the the implications of these sorts of ideas. Okay, so the two ideas are scale-free networks and the friendship paradox. We're going to start with scale-free networks. So the idea is that, if we look at the degree distribution, I'll show you an example of this in just a second. So, you think of what degree, how many edges does each node have in a network, and then you do like a histogram of that. So this many people have 1 degree, and then slightly less have 2 degrees, or maybe it's a normal distribution, right? Like a bell curve where most people have about 50 friends, and a few people have way more, and a few people have way less. But there are a lot of cases and a lot of kinds of networks, including human networks, where these degree distributions are really, really skewed, where many people have very few edges and a few people have very many edges. So why might this happen? I mean, I think there are some examples that should come to mind pretty quickly. Like number of Twitter followers, for example, is very skewed, right? A few people have maybe tens of millions of followers, while most of us have many fewer than that. So what could cause this sort of degree distribution of this really high skew? I mean, one answer is rich get richer processes. So this is, sorry about that. Just a second. Okay, sorry about that. So one answer is rich get richer processes. So in the network literature, this is often called preferential attachment or cumulative advantage. Another is called the Matthew effect. So from the Bible, the book of Matthew, the idea is that those people who have get more, and those that don't have get less. And so there are lots of processes in the world that work like this, for better and usually for worse. One of the famous examples, the person who came up with the Matthew effect talked about scientific, like the number of citations that someone gets, or the number of grants that someone gets as a scientist or as an academic, often is really predicted well by how many they've had in the past, right? Because as you get attention, as you get grants, as you get citations, as people think that your work is good, you then get more resources, right? Better students want to work with you. Other grant funding agencies will hear about you. And so therefore you're more likely to have better resources to then do better in the future. These sorts of processes, so websites are famously examples of these scale-free networks. As a website gets more attention, it may get more ad dollars, ad revenue, right? Which means they can hire more developers to make a better website, or hire more salespeople, or pay more for ads, etc. And so, and they get more revenue. And this is even compounded for things like Google, where we're having more visitors, maybe they train our algorithm better and they make a better search engine, etc. And so there's lots of reasons and lots of contexts in which we might think that having resources leads to having more resources. And so the other question that you may be asking, why are these things called scale-free networks? I promised I would show you what this distribution looks like. So the reason they're called scale-free is because no matter where you zoom in on the distribution, it looks the same. It has the same highly skewed shape. So this is a random network. They call it a Barabashi-Albert network. They are the ones who came up with some of the mathematical pieces of this. And so if you look right here at the top, this is how many nodes have each degree. So, of all the nodes, this then counts, right? It's sort of like a histogram. So about 1,600 or something nodes have degree of 2. So in this version, has to have a degree of at least 2. So have at least 2, and then it drops off really, really quickly. So by the time we get even down to 50, it's like basically nobody. It's almost 0. And so by the time we get to, it really looks like by the time we get to about 5 or 6, it's really, really low. But this hides like a surprising fact. So we might think, for example, that if we just got rid of those ones with 2, like it looks like there's just a whole bunch of people that have a degree of 2, and then everybody else has pretty low. So if we got rid of those 2s, we would see that it's actually really, a lot closer to the same. But once we get rid of 2s, this is a graph that has nodes of at least degree 3. Now, instead of the y-axis going up to 1,500, it goes up to about 700, but it's still dominated by nodes with degree 3. So we might think, well, what if we got rid of the nodes degree 3, and then we could see what it's like with degree 4. This is degree 4. Again, it's about half as much. Now we're down to about 350, but it's still dominated by degree 4. And this pattern, this is the reason it's called scale-free, the pattern will continue. That is, in a hypothetical universe with like infinite number, no matter how we zoomed in, we would see the same shape. If we zoomed in on just those with over degree 50, we would see there might not be very many of them, but there'd be way more than there are 51 or 52, etc. So that's a scale-free network. So what are the implications of this finding? That these, not only this kind of mathematical concept of these networks, but more importantly, the empirical reality that these networks exist and they're common in the world, in the sense that there are these highly skewed degree distributions. So one is really positive, and that is that these are robust to random failures. This is from that, you saw actually a video of Laszlo Barabashi talking about this, that if what this means is you can think of as like they're hubs, right? You can think of airline networks are another great example, that there are hubs where there's lots of flights into a few cities and few flights into many cities. Routers on the internet are also examples of this. One of the great things about this is it means that they are robust. So if any given airport is just as likely to experience, for example, extreme weather, which is probably, it's not really true, but it's not too far from the truth. And any airport might be shut down. Chances are it will not be a hub that gets shut down. If we randomly chose one airport that would be shut down, it would be a hub. If we randomly chose one router on the internet that got shut down, chances are it would not be one of the important ones. And you can really easily kind of route around any problems because they have pretty limited impact. So that's a really great implication of these sorts of networks. The other one that I wanted to bring up is that from a moral standpoint, that when we think about the outcomes, they are not fair. In the case of the random graph, and I'll show you another example of these. We know obviously in these cases that it's literally random, right? There's not like a node that's like smarter or better or harder working than other nodes, and therefore it's the one in the center that gets the resources. And yet we still see, right? Maybe that's a good way of thinking about it. Even though we know that it's completely random and all nodes are literally equal. There's nothing different about them. One gets much more attention and many more resources. And this sort of rich get richer effect is sufficient to explain that. In the real world, this is not a there is likely a correlation, right? That the people who have the most wealth and the most resources and the most social capital, may have some attributes that help them to obtain those positions. But the reward that they get, right? This cumulative advantage, because you were successful in the past, you get to be successful in the future. Far outweighs any minute differences that might exist, if that makes sense. We know, for example, let's say that intelligence is the only thing that mattered for your future. Innate inborn intelligence was the only thing that mattered for your future earnings. And we know that intelligence is like a bell distribution, right? A bell curve, a normal distribution. And so most people are right about in the same. And even those that are, higher intelligence are not that much higher than the rest of us. We're all, about the same. But when we look at income, there are people who make billions of dollars or, hundreds of $1 million per year, while most of us certainly make much less than that. Most of us are in sort of the tens of thousands of dollars per year. And so the difference in innate ability and in the kind of the inputs are way larger when it comes to the outputs. So that's one way of thinking about it. And I think this relates to, we'll talk about this a little more at the end of this semester. But when those advantages are passed on, for example, over generations and are compounded by racial disparities, you can see that there comes to be an even greater kind of unfairness, injustice that's in the world, and that can get perpetuated through these sort of processes. That's the idea, right? That whenever these processes of rich get richer exist, then there's sort of an inherent and innate unfairness. That anytime you can make small differences early on can lead to kind of compounding differences later on. Okay, so that's the idea of of scale-free networks. The other concept that I'll try and be quicker about is the friendship paradox. So this is a really cool, kind of fun idea, but it has, we'll talk about some neat implications and some important implications. This was discovered by Scott Feld. He is a member of the Purdue Sociology Department. He's great. The big finding is that on average, your friends have more friends than you do. This is a little depressing when we think about it, when we first hear about it, that you are, on average, less popular than your friends, which it seems like, what in the world? Like, how can that be possible? Like, I am about the same as my friends, so I think I should be about the same, have the same number of friends as them, right? I'm not like way less cool than them. All right, maybe in my case, but in your case, not. Okay, but the key idea is that people, there's like this, we saw these degree distributions, right? People who are connected to lots of people are more likely to show up in friend networks. Like, they show up in lots of people's friend networks. If you think about who is your friend, well, these people are friends with lots of people, they continue to show up. And this is, I'll try and say it one other way, that you are likely to be friends with people who have lots of friends because they have lots of friends. And so anytime we're kind of taking, averages of friends, these people are likely to show up. And people who don't have very many friends are not likely to show up. And so if we're thinking about, if we're asking, how many friends do your friends have? Well, the people who don't have very many friends probably aren't your friend. This is a subtle, strange idea. Let me show you an example in just a second. The effect is much more pronounced as the skew changes. So let's say, as a totally extreme example, that there was somebody, there's this group of 10 friends, and there's someone who's friends with everyone, like a star network, right? Everyone only has one friend, and that friend has 10 friends. And so if you think about the average number of friends that your friends have, it's much higher. Everyone's average number of friends is, 1, except for that one person who has 10 friends. But everyone else is, but everyone is friends with that person, right? So your friends' average is going to be 10. Hopefully that makes sense. I'll show another example in just a second. So this can, maybe another example that helps to, make this intuitive. If you think about the people you follow on Twitter or Instagram, they're likely much more popular than you, right? You follow them, and they have more friends. They have more people that are followed by them than you do. So here's an example. Here's an actual graph, a random graph. This is the degree distribution. In other words, how many friends each person has, right? So these two in the middle have 7 friends each. Everyone else has 2, 3, or 4. And then this is hopefully you can see this okay. This is the neighbors' friends. On average, how many friends do your neighbors have? So if we look at for example, these two here, they both each have 2 friends, but their friends are these 2 people that have a degree of 7. And so their friends have 7 friends. So I've colored these. Everyone whose friends have more friends than them, in other words, their neighbors have a higher degree than they do, is colored green. And it's only these 2 in the middle that already had very high degree who don't have more friends. And so if we look, for example, let's just look at one more example so that you can get this. This person has 4 friends, the 2 7s, and then this 2 and this 2, right? So even though 2 of their friends, half of their friends, have fewer friends than them, they are also friends with these 2 7s. So 14, 16, 18 divided by 4 is 4.5. So that's why theirs is, they have fewer friends than their friends. So in other words, these 7s, they show up in almost everyone's graph. So every time you're taking this average, you got to add that 7 in, therefore increasing the average. I was going to say they show up on everybody's. I don't think they show up on this person's. So there you go. So people that have lots of friends show up over and over again in people's friends networks. Really by definition. So what are the implications of this weird paradox? It seems like sort of a kind of a statistical trick, just a silly trick. Well, in a lot of cases, we don't get to see the total distribution of a network and who's most popular. It's hard to detect. Life is not like Twitter, where we get to see how many friends people have. And so one approach to figuring out who the most popular people are is to choose a node at random and then have them choose one of their friends at random. And that those friends of the random person are more likely to be popular and to be closer to the center of a network. And so what? Therefore what? One reason that I believe was in the readings, one thing you can do with this is something like detecting an outbreak. So there's this great study by, I think, Nicholas Christakis, where they looked at friends of friends and then saw that they, when there was this flu outbreak, they caught the flu earlier than sort of the random network. So the random network's friends, the random people's friends, caught the flu earlier than they did because these people have more friends, they're more central in the network, they're more likely to be exposed to the flu. And so you can do things like detect outbreaks. You can also do things like focus interventions on these people. If there's a message that you want to get out to more people, then focusing you can it's a very cheap way, right, of figuring out who might be influential is just ask who is your friend and then focus on those people who are people's friends. Ideally, even if you could ask people, who is your most popular friend, right? That gets you pretty close with very little data, very little effort. Okay, so those are these 2 ideas. I hope that's helpful and look forward to chatting about it with you.